Right. Hi, everyone, and welcome to the Cambridge Cheminformatics meeting. We are being hosted very kindly by CCDC today. So before I take you through the program, I'm going to hand you over to
me, that's Jonathan. Welcome to CCDC. For those who know me, I'm Jonathan Betts, and I have the pleasure of two things. Firstly is, for those in the room, fire safety, all important. So hopefully everyone here has signed in by the app tablet at the front. If you haven't, please go and do so. Please remember to sign out on the way out. That's the first thing to remember. No fire drills for the rest of today, so please follow a CCDC staff member if you need to exit, and they'll probably spring up in high-vis jackets. If anyone has accessibility requirements, please probably come and find me and we can help out. And car park out there behind the posts as shown there. Secondly, you go on to the next. I'll hold it a bit more. CCDC is delighted to be participating in the Open Cambridge initiative. So the inaugural event is next Wednesday, Cambridge Wide Open Day. Hopefully many of you already heard about it. This is very much around inspiring collaboration within the Cambridge cluster, both scientists, individuals, members of the public. So we're trying to grow those connections, grow awareness amongst all the fantastic organizations and individuals that operate within and around the cluster here. So we've got a range of activities going on. You're all very welcome to come along or spread the word. So we've got some of our educational activities being run. So that's all about understanding the science of chocolate or using Lego to understand polymorphs. Through to some demonstrations of our tools. So I have the various demonstrations taking from molecule to medicine, and then a presentation around how we work to try and bridge the various organizations involved in our broader community. So there is, you can't see it on there, but there is there should be a code. It's actually blocked off by the you can scan in there to that's the one. So if you are interested, you can go to that URL. I think people might want to capture that before we move on. And yeah, please sign up because we need to know who's here coming on the day. Thank you. I'll hand over to the real stuff now.
Thanks very much, Jonathan. Just make sure that the online. Hi, sorry, Andreas, could I just check that the microphone is working on the Zoom? Just no, not that. You could hear me before, but it just doesn't seem to be picking up. Hi. Hi, Andreas. Could I just check that you can hear us? Oh, they can. Okay. Great. Sorry, guys, false alarm. So yes, Charlie Harris is here, and he's going to talk to us about diffusion models for structure-based drug design.
Awesome. Thank you very much. Can you all hear me? Amazing. Well, there's a saying in machine learning that the hard stuff is easy and the easy stuff is hard, which I think we just proved. But yeah, thank you very much to Andrew and Andreas for inviting me here today. If I'm correct already, I'm actually co-supervised by Tom Lundell and Pietro Leo in the computer science department. And it's the latter where, yeah, I end up spending most of my time. And I'm second year PhD, I'm going to be talking to you about structure-based drug design with Equivariant diffusion models. So first of all, what am I? I'd like to say I'm something between a computational biologist and machine learning scientist. So about half my work is in computational biology, structural biology, drug discovery. Oh, sorry. This is actually what my training was originally in. I originally trained as a biochemist, and then I somehow got into this machine learning stuff. And so during this talk, and even in mid-sentence, I might swap hats between my biochemistry hat and my computer science hat, depending on what I'm trying to decide. And full disclaimer, I'm used to giving talks to undergraduate computer scientists and not real cheminformaticians. So I might spend a bit longer on the machine learning stuff than I usually do. Very quick overview, plan for this talk. I'm presenting work from 2 different papers. It does this sort of stuff, which we'll get into. First one is called Structure-Based Drug Design for Diffusion Models. And we did a second follow-up paper with some extensions, which this is one of the first times I'll be presenting. So very quick overview of some of my work. There's really 2 pillars to my research. First one is generative modeling for molecule design, and the second one is machine learning, studying protein dynamics. And we'll be talking to you about the first one here today. So very quick, machine learning 101, in case you have no idea. You can think of these models as sort of a black box learning function. So we can take in some inputs, suppose images of cats or dogs, and then a lot happens in the middle and we get some output, in this case, either a cat or a dog. How this is usually done is using something called a neural network, which is these biologically inspired machine learning models, which has these neuron things here. And inside of each of these neurons is actually just little functions with numbers that we can tune. And then afterwards, there's basically what's called an activation function. That means this is either giving out a 0 or 1. What's powerful about this is, can you see my mouse? Yeah. What's powerful about this is if you stack lots of these neurons together with all of these little step functions, you can then approximate very complicated functions. Like you see the blue line here. So suppose X is some sort of molecule design space and Y could be activity. Now, there's a theorem called the universal function approximation theorem that says theoretically this architecture on the left you can see here can learn any function. It can be, is this image a dog or protein folding, whatever, with a few caveats, one of which is that the model has to be infinitely wide, which we don't have a computer that can do that yet, and you need infinite data. So in short, these models are very powerful. If you have very large numbers, very large models with a large number of parameters, think, GPT-4. Lots of data, and ideally lots of good data. We'll get into that in a minute. A lot of good inductive biases. And so basically these are things that we know about the data to be true, then we can basically build these assumptions into our models that make them more effective. So for example, a neural network that's designed to work over images is going to be different from one that's designed to work over molecules. And I'll speak a bit about that later. In particular, I'm going to be talking about a sub-branch of machine learning called generative modeling. So if machine learning was just glorified curve fitting, generative modeling is basically glorified distribution learning. So suppose I was trying to make a generative model that can make images of dogs, like you see here. Each of these images just have coordinates, pixels, sorry, with different values. And we can plot the distribution of all these values over some simplified 2D space. We can see that the real images of dogs tend to be clustered together in certain regions. And we call this the true data distribution. But the problem is we don't know what this is. So we define something that we call a model distribution. that we can say parameterize with a neural network. And then what we can do is basically minimize the difference between find some way of minimizing the difference between the true data distribution and our model distribution. And all being well with the quality of the data and the training, we can train a nice generative model. So once you've done this, you can do two things. First one is probability evaluation. So given some input feature X, suppose this photo of a chihuahua, you want to know, is this chihuahua likely to be a photo of a dog or not? We can evaluate it using our learned model distribution, and it should give us a high probability value. We can also give it this similar looking but different photo of a muffin, give it to the model, and then all being well, it should tell us that this is low priority. And finally, the last thing, perhaps the most exciting thing, is the fact that once we've learned what this distribution is, based on the true distribution, we can then sample novel data points, which in the case of dogs tends to be quite high quality because we have lots of very good images of dogs. And then as you move into different domains such as molecules, your results can vary. So very quickly, previous deep generative modeling work for molecular design. This is a figure from a very famous paper in this space. So imagine if you had some encoder, decoder set up. We can train this to learn from a large database of molecules. So we could take true molecules with perhaps properties that we like. We train some, so I should say this is an autoencoder. So we first encode this molecule into some low dimensional latent space. And then we can train a decoder to reconstruct that original sample. And then this is nice because what we can do at the end of training is throw away the encoder. Now we just have this low dimensional latent space that we can move around in and sort of optimize and explore and interpolate new molecules. But this is old methods now. So previously, before the whole diffusion modeling thing came in, there was kind of two paradigms for generative modeling for molecule generation. There was the all-at-one approach, where we basically just sample some little bit of noise, pass that through the neural network just once, and then out at the end, we get a molecule. And there's a node-by-node or autoregressive approach, where we have some partially completed molecular graph, and we just iteratively sample from noise, either to add a new atom or a new bond until we have a whole molecule. However, there's some problems with these things. So in the case of the all-at-one and one-shot approach, we're assuming node independence between all the atoms in the molecule, whereas obviously we know atoms tend to only be stable in certain configurations. Problems with the auto node-by-node approaches is we need to define some arbitrary ordering of all the nodes in the graph, which obviously we know molecules don't have those. And then that leads into the last problem, which is that if you do it node by node, different generation traces, so orders in which you add atoms that lead to the same molecule, can't be easily evaluated equally, which makes them very unstable to train. So I'm just going to talk about some ideal qualities that you might want given these problems. So the first one is that we would ideally like to model interactions between all the atoms iteratively as we're building the molecule. So if you're aware of like the structure module in AlphaFold 2, it's essentially just applying the same neural network over and over again to the protein structure under the hypothesis that it's not going to get it right first time, but if we reapply the same model 8 times, we can iteratively refine our molecular hypothesis until we get a nice structure. Lastly, we want to be fully order and permutation equivariant. That's just a fancy way of saying in a computer, you need to number all of the atoms arbitrarily. If I was to jumble those numbers, do I get the same output from the model, or does the model get thrown off by that? And lastly, evaluate all the probability of all molecules equally, regardless of the generation trajectory that we actually took to get there. And hopefully I'm going to be describing something to you that satisfies all of these constraints. So that brings me onto the actual work that we've done. First paper was structure-based drug design, Equivariant diffusion models, which wasn't just me, it was a combination of all of these amazing collaborators here, who I'm very lucky to have. So I like to go through, take your photo, cool. I like to go through, to explain sort of this method, I like to break down the title and explain it bit by bit. you all know what structure-based drug design is, but just very briefly, we're basically rephrasing this problem of designing ligands in pockets in a simplified way to basically learning the conditional probability distribution of generating certain molecules given a fixed target receptor, and we're doing this all in 3D. Equivariant. So this is basically a term from the field of geometric deep learning, which is specifically the application of deep learning to learning objects that inhabit geometric domains, where domains is just a fancy word for spaces. So these include grids, don't worry about groups, graphs, and don't worry, geodesics and gauges are basically surfaces. So there are actually now people who can do basically deep learning on protein surfaces and the chemical features on them, under the hypothesis that this is what governs molecular interactions. Grids, basically just images, and obviously as machine learning person, we're quite interested in graphs because they're a very natural way to represent molecules. And so we can learn on these molecules using a type of neural network called a graph neural network, where basically, obviously this is just some arbitrary graph, but it pretends it's a molecule. We have each of these nodes, A to E, with node features, in this case XB. And what we do in every layer of the neural network is basically take in as input the current node features of node XB and the features of all the nodes that are in the neighborhood, in other words, connected to it by bonds, for example, of nodes XB. And then we use that to create some sort of learnable function that allows us to iteratively basically transform the learned representations stored within the graph on the hope that these representations will then be useful for something downstream. So for example, predicting binding affinity or toxicity. And in each of these learnable functions in every node, there's just a little neural network hidden as well. So what does equivariance actually mean? So obviously, when we define, say, a protein structure, we need to give it coordinates, but those are just completely arbitrary. If I was to move the protein or rotate it, it would be exactly the same protein. So if, say, you're doing protein function prediction, you would want the outputs that you're predicting to be invariant to rotations and translations. But in our case, what we're essentially doing is inside a pocket learning the probability field where we can generate molecules. So as we shift and rotate the protein, we want that probability field to be shifted equivalently. And this property is known as equivariance. It's been a very big thing in machine learning in the last few years. And I should just say as well, if you want to be technical, the combination of rotations and translations is called the SE3 group, which you might see hanging around later. Diffusion models. So very quick, just quick show of hands, who's heard of the diffusion model? Knows how one works? Cool, okay, I'm not redundant. So they're a kind of latent variable model that have become very popular in the last 1 or 2 years, obviously. So very quick high level overview how they work. You can have some data, can be an image, can be a picture of a dog, can be a molecule, doesn't matter just yet. And what we do is over many time steps, usually about 1,000, we slowly add Gaussian noise to this data until it's been completely destroyed. There's no distinguishing features from the original data left in this image, which sounds really weird until we say that basically we learn a model, typically a diffusion model, that basically learns to map back from this noise to new, hopefully high quality sample data. To be more precise, we can find in Markovian diffusion models, Markovian chain of random diffusion steps, gradually adding noise to sample data until it loses all of its distinguishing features. And then a model, typically in your network, is then trained to reverse this process. So just to be confusing, the image direction is now swapped. So here we have some sample image at time step 0, so we'll call this x0. And then from going from right to left, we slowly add noise until time big T, where T is usually about 1,000. And we can define this forward diffusion process here as Q of Tx given T minus 1, where we're just adding Gaussian noise at every time step. And then what we can do is learn the reverse, or in other words, generative diffusion process that we call P with parameters theta. that learns to go in the other direction. And what this tends to equate to is we're basically just predicting the mean of the noise that was originally added to that data, and then the variance used to be learned, but now usually people fix the variance according to some variance schedule, and that itself is a very big area of research. So what does this all mean when you can actually sample from it? So this is an example of the diffusion model making an image. So you can see it starts off very noise and goes to some new sample data. But what's actually happening here is we're just basically turning a really simple distribution into a more complex distribution. If you look at this the trajectory plot on the right here, if you were to just take one pixel of rows from here, what you would find is this is basically just a normal distribution. So there's no very low probability here, and then you have a normal, very high probability here, and then low probability. And then on the very far right, we have a simple but slightly more complex distribution that just has two normals, two peaks with less sort of spread. And what we can do is then sample from anywhere in a normal Gaussian, which we can very easily do on a computer. And then what we're effectively doing at every time step is we're following a trajectory that's gradually turning this really simple distribution that we can easily sample from onto a computer into a more complex distribution. And obviously this distribution is usually in very high dimensions. So another way you can think about this is to go from basically xi to xi plus 1. What we do is we just take the current state of the data at xi, ignore exactly what this means just yet, just pretend this is our reverse process. So this is the noise we're removing from the data. And if we were to just simply do this, we would basically always just be, our trajectory would always just hit a mode of the training data. So we would have zero diversity in the samples that we get from the model. So basically we just do essentially Langevin dynamics and just add a small bit of noise to the sampling process, which is why all these lines are wiggling here, such that this noise is usually small, such that you always end up in a high probability region, but you don't always hit the same point on your target distribution. I'm skip through this very quickly. Long story short, how you train this, how people used to train them is using something called the variational lower bound, which I won't go into. However, people actually train them is you're basically just minimizing the difference between the true noise that was added to that data and the noise and your predicted noise, which you predict for neural network epsilon theta. I'm just a bit aware of time, so I'm going to skip through this as well. So finally, moving on to diff-SPDDs, so diffusion model for structure-based drug design, sample molecules in pockets like this. So a very quick overview of how the method works. So this is a similar figure to what you saw earlier. So you can see on the right, we start with protein ligand complex as our training data. This can either come from the PDB or unfortunately machine learning people use synthetic data sets, which I'll get onto in a minute. And basically this molecule here, the ligand, from a machine learning perspective, is essentially just a graph that has two features, our coordinate features, which are called X, and the node features, in other words, atom types H. The concatenation of these we call Z. So we take Z, time equals 0, slowly add noise to both the node, to the atom types, and the coordinates themselves, until we've basically just completely exploded the ligand in the pocket. And then we train a model to reverse this process. So more specifically, what we're learning is the transitional probability distribution from Z at T to Z at T minus 1, conditional on the fixed structure of the protein receptor P. And then this prediction is actually done with a neural network epsilon theta that takes as input the ligand, the protein, and the current time step T. And this epsilon network is an SE3 equivariant graphical network, which I mentioned earlier. You can sample from it, you get stuff like these. Some of these are good, some of these are less good. We can talk about that a lot later, I'm sure. However, I wanted to bring the attention to this example here, which I quite liked. So this, basically, I should say, in these diagrams, every row is a different target. The molecule in magenta on the right is basically the one from the test set. and then the green ones are ones that we generated with diff-SPDD. The ground truth one on the right has a tricyclic ring system designed by conventional SPDD methods to maximize shape complementarity to the pocket. And we found that our model generated one quite similar ring system. I really like this example. So this is the same model, but trained on a different data set. You can see that the molecule in the test set is basically just an aliphatic fatty acid chain. Obviously, a million reasons why this wouldn't be a good drug molecule, but when we sample from it with diff-SPDD, it's basically learned the classical medicinal chemistry move of adding rings along the chain, which, as you all know, reduces the number of rotatable bonds and binding and so forth. This table is completely meaningless. You just need one to get published in machine learning with your numbers highlighted on it. I'm being a bit facetious, but in all seriousness, we do fairly well in terms of mean Venus score, even though the standard deviations basically show you that these metrics are all meaningless, and I'll get onto that later. And then in terms of QED, SA score, we're all basically similar to all other methods. So I think, long story short, I think we're getting quite data set limited as a field, as a conclusion. Yeah, I can take from that. So that's a natural place to just pause for 1 minute in case anyone has any clarifying questions. I would leave speculative questions to the end. No? All right, fantastic. So yeah, so we did all this work, and then we've done some follow-up work and published a paper called Flexible Small Molecule Design and Optimization with Equivariant Diffusion Models. So long story short, for, within structure-based drug design, there are a lot of other things like, fragment linking, scaffold hopping, which for the sake of the computer science undergrad that reviews most of my papers, I just call SPDD subtasks from now on. There's a lot of methods such as, D-linker can do fragment linking with machine learning. And I call these conditional methods. So this is where we train a model basically on lots of, say, pairs of fragments as inputs, and then you supervise it to predict a linker in between. However, these have a few problems. Usually these conditional models are trained on synthetic data sets. And so there's not, for example, many real structural data sets on scaffold hopping. So you just have to create them synthetically by masking atoms. Specialist models don't generalize to new tasks. So for example, if you train to do fragment linking, you can't do scaffold hopping, which basically means you have to limit the amount of training data you can use. And you also need to pre-specify atom attachment points. And so in ideal world, we like to train on all protein drug data. You can generalize to any arbitrary task, can automatically learn where to place atoms without instructions. And hopefully I'm going to present to you something that does that. We use a strategy called inpainting, which is very popular in the field of image synthesis. So you can imagine this is basically where, suppose you have an image, you can mask out some bit in the middle, and then basically, so based on the surrounding context, you can fill in that missing part of the image using some model. And we adapt this basically for structure-based drug design. So suppose you have protein atoms here in gray, and you have some fragment in orange inside of it, and you want to build around this fragment. Pardon me. What we can do is during the denoising process, so say this is ZT here, we can denoise one step, where I should say the orange are the fixed atoms, the green are atoms that we're generating. We then define a mask that tells the model where the fixed region is. And so we can mask out the region that we want fixed. And then what we can do is take the structure that we want to be fixed, noise it the appropriate amount of steps until time equals t. Use an inverse mask to get basically the noise representation of our fixed structure, and then merge these two together. And then this way, as far as the diffusion models is concerned, this is all within distribution. It's not aware that I've injected in this fixed substructure. We can iteratively repeat this until we're guaranteed to get out our fixed substructure that's not moved or changed in any way, and we can design new atoms around it. The nice thing is, as well, is that this denoise step is just done with the base diff-SPDD, essentially just train on the whole PDB. You don't need to retrain any new models to do this. And so this means you can then, just by defining arbitrary masks with, say, RDKit, you can do a lot of things. So we find it works for fragment linking quite well. say fragment linking. This example here is basically a monster fragment link, because basically what we've done is generated a whole new fragment in the middle and then designed 2 linkers on either side. Same with fragment growing. It's nice to not have to explain what all these things are. Fragment merging. This one is slightly more intricate, because basically what I did here was fix these regions, fix those, and remove an atom, and then we were able to merge them together. And the magenta here is the same molecules merged with Fragmentstein. Scaffold elaboration, we found it works very well for scaffold hopping as well. There was a technique, which I won't dwell on too much, called resampling, that we found was absolutely critical to get this working. And we can show these here, like showing these just examples of different designs. Sorry if I go on for one more minute. Cool. I'll skip this because it's less important. So this is stuff I'm actually working on at the moment, and basically it's to answer the following question. So everyone, including myself, makes all these molecules for structure-based drug design, where we generate molecules in 3D on the implicit assumption that if you generate a molecule and a pose at the same time, then that's great. You don't need to do docking because the pose should be fine, right? But then everyone evaluates the quality of the generated molecules, and no one evaluates the quality of the generated poses. So what usually happens is something like this. You take some protein linking complex data, train a generative model, you sample from it, get a generated pose. You then usually redock that molecule, no idea what's going on there, and then we usually just remove the pocket and we evaluate, using important things like QED, assay score. And then usually, so this whole generated pose and redocking process is usually not very transparently communicated. So this whole what's happening here is basically just completely blurred. And the only thing that we know about is mean Venus score. So is this talk being recorded? You can ask me in the pub afterwards. But this is from an actual paper that was accepted at one of the most prestigious machine learning conferences in the world, basically just saying our method has highest mean Venus score, therefore it's the best, with no standard deviations. And I know for a fact the standard deviations are about 10 times larger than the difference in these scores in the first place. So yeah, as a field, I think we have a problem. And so I'm doing some new ways of benchmarking these models that will hopefully reveal some of the failure modes in ways we can solve them. So this is counting steric clashes, which for the diffusion-based models, including ours, by far the worst, we found out. And interestingly, as you would expect, redocking them fixes those. This is the same. So for this, we're basically calculating the strain energy of the generated pose, which I guess you all know what that is. This green line here is basically the training set that we use. So you should at least be above or below that line. And you can see basically all the methods do absolutely horribly here. Don't take these energy values seriously. That's the combustion of TNT. So I don't think this is real. This is basically just showing that the poses we're getting out are so far out of distribution to what the force fields are expected to calculate that you just get these exploding values. I've just torpedoed my whole career up to this point, but I think there's a lot of interesting problems to still working on. I'm still very confident we can find solutions to them. I don't know this on my own. This is all possible thanks to all these amazing people. And yeah, thank you very much for listening.
Thanks very much, Charlie, for a great talk. I'm not sure we have, but maybe just time for one question if anyone wants to ask. Anybody?
Not yet. No, with Tom's group, we are looking at it. But then, yeah, that's years of evaluation, whereas machine learning experiments usually take months. There has been some people who not 3D structure-based drug design, but people that use like smiles-based stuff, like reInvent, they have done that. But in terms of like the really modern machine learning approaches for structure-based drug design, no. And it's not good, if I had to guess. Oh yeah, sure. Sure. Right. All right. Thank you. Let's thank Charlie again.
And our next speaker is Kohulan Rajan, who is a postdoctoral fellow at Friedrich Schiller University, Jena in Germany. And Kohulan, if you could just share your slides, please.
Yes, one moment.
He's going to talk to us about extraction of compounds from the chemical literature.
Okay, very good. Share. Okay, can everyone see my screen?
Yes, that's great. Thank you.
Great. Yeah. So thank you, Andreas, for the introduction. And I'll be talking about DECIMER. DECIMER is for deep learning for chemical image recognition. So I'll be talking about how we started it and what's the current state and how everyone can use it. The information which is readily available in the text form in journals, which could be mined using various different text-based tools, but also we do find quite a lot of chemical structures in natural product journals and more medicinal chemist journals and so on. And these 2D representations are human interpretable, but not machine readable. How to get these structures into a machine readable format is a question which we trying to resolve for last 30 years. So the initial tool to work on this sort of questions was developed in like 30 years back, which was known as OSRA, which is an open source toolkit. And there were few more methods and toolkits which are rule-based and available to open public, which does very similar things, which are scanning, vectorization, and character recognition, graph compilation, and so on. We talked about this very clearly in the paper which I've been showing here, which got published in 2020. Meanwhile, there were quite a lot of movements towards deep learning-based solutions. With that, we also ventured into this problem with the DECIMER project. So DECIMER basically takes a journal article like this, tries to scan through it, detect the structure, and segment it out. Once the segmentation is out, we try to predict the SMILE strength of the segmented structure, and which we could redepict or reuse or later use it to update the databases which are already available. The whole project is known as DECIMER. DECIMER currently have 3 components. One is segmentation, one image classifier, and the image transformer. Segmentation was developed with my friend and colleague Otto Brinkhaus. We published this paper in 2021 in Journal of Cheminformatics, where we talk about a segmentation algorithm which actually detects the chemical structures from a printed literature, segments it out, and cleans it and presents it back to the user. So this toolkit also made available open source. The core part of the toolkit is the masked RCNN model. Masked RCNN model is a region-based convolutional neural network model, which was published in 2017. What it basically does is when you have an image like this, which I'm presenting here, it tries to scan through the image and tries to detect the objects in this image. In this case, we have trucks and bus. Once it detects all the objects, it tries to create masks around the objects, and later we can use the masks which are created around the object to segment the objects out of a bigger image. Similar to that, we could also segment the chemical structures out of image presented or PDF presented. In order to train the model, we had to manually hand annotate nearly 1,000 articles. We ended up annotating around 2,000 images. We created nearly 9,000 annotated regions. And then all these annotated regions comes from Journal of Natural Products. We retrained the whole mask-CNN model, and then we deployed it in our toolkit. So usually when we try to detect and segment out, most of the time the mask works well, but sometimes it ends up creating a mask which is not complete. When you have incomplete masks, what it happens, it tries to segment out a partial chemical structure, which is not usable. In order to overcome this issue, auto-developed binarization and the expansion algorithm, basically what it does, it takes the original mask and then it tries to binarize the image with the mask, and then it dilates the image. Dilation basically fills up the gap. You could see in this image, there is oxygen and a double bond, it fills up the gap. So it makes it a single object, and then we try to expand the mask little by little, by pixel, when it reaches, until it reaches complete white pixels. Once it's done, it gets, the algorithm reverts the mask back to us, then we take this whole mask and segment the complete chemical structure. How well this works on real world data is shown here, which is basically tested on 25 articles, each from 3 different publishers, even though our model was only trained on Journal of Natural Products. These 3 different publishers, our segmentation model performs similar. You could see only with the model we could achieve 80%, and with the model plus the mask expansion, we could nearly segment out 100% of the structure from the printed literature. But most of the times we also did end up getting wrong segments because they look similar to chemical structures, but they are not. How to overcome this issue then comes in the DECIMER image classifier, which was co-developed with my colleague Isabel from the University of Prague, where we have a binary image classifier which was trained on chemical segments, like chemical structure segments, and also images found on the public domain. And then the image classifier, once the image classifier was trained completely, when you give a segmented image or a non-chemical image, it tries to determine whether this image given by the user is a chemical structure or not. The whole image classifier was based on the EfficientNet version 1 published by Google in 2019. The whole image classifier was trained on the Coconut database and also Campbell database for the chemical structures, which was generated using our in-house developed RANDEPIC toolkit, and 6 million of images was downloaded from public domain data sets, which are available to the public. So when we looked at the external testing, our image classifier was near perfect in most of the test cases. And this is now included part of our platform. And then this also, the code was packaged and also made available to the public through GitHub. Moving on, I'll be talking about the main component of our work, DECIMER Image to Smiles. DECIMER Image to Smiles was first started looking into the show and tell paper by Google published in 2015, where they included 2 different architectures, an encoder model, which is a CNN, and a language generating RNN model. So what it does, the encoder tries to encode the image into a latent space, and the language generating RNN takes the latent space vector and tries to make into a meaningful sentence. So here you could see there are a few people standing, they're trying to sell something. So it tries to detect all these objects separately, and the language generating RNN tries to put them into a meaningful sentence. Using the similar method, we developed a DECIMER image to SMILES where you present a 2D chemical structure and it tries to generate a SMILES string. This initial work was published in 2020 called DECIMER Towards Deep Learning for Chemical Image Recognition, where we basically open sourced our work and said that this work could lead to a better open source optical chemical structure recognition. But still, we had a lot of development to do in this work. This was a preliminary communication. Later on, one of the hurdles we faced during the whole process of training and getting the model out was the training time. When we tend to train nearly 15 million data points, it took us 26 days or a month to train in a local hardware or the cluster what we have here in Jena. So similarly, when we increase the data set like threefold, the time also approximately increases threefold, which is 3 months, which is not a feasible time frame. With that, we actually switched to the latest hardware developed by Google called a Tensor Processing Unit, which is available to the general public through their Google Cloud platform, where we optimized and rewrote most of the scripts to train on the Tensor Processing Units. Why we actually started using Tensor Processing Units is a simple example which I'm giving here. When you tend to train 1 million data point on a NVIDIA V100 Tesla GPU, which takes nearly 30 hours to train, this could be narrowed down by using a TPU single device version 3 by 4 times faster. And if you use a device with 32 nodes, it's 16 times faster. And the latest hardware which Google allows us to use is the version 4 of the TPUs. It's almost 8 times faster than the original GPU training. With that, most of our models are moved to TPU training. And then also, the second thing which we looked at was the chemical language representation. So there are 3 types of major syntaxes available, which is SMILES, deep SMILES, and selfies. SMILES, most of us already know. Deep SMILES and selfies were developed in order to train deep learning-based models. Which string representation to use and which one works better for us, we actually talked about in a nice article which got published in 2021 in Digital Discovery, where we explain which string representation works well for us. With that, then the third thing we looked at is how to generate diverse chemical structures or chemical structure depictions. In order to do that, my colleague and friend Otto actually came up with a tool called RANDepict. So here what we are trying to do is we use CDK, RDKit, and Indigo in order to generate a wide variety of chemical structure depictions with all sort of bond lengths, bond thickness, different atom numbers, abbreviations, augmentations, and so on. Most of the augmentations which are shown here are included in the toolkit, and we try to generate a variety of depictions. So here in the GIF image, you could see that caffeine structure is depicted with different sizes, different augmentations, and all this data could be generated using the RANDepict toolkit. RANDepict also could generate Markov structures. So if you have a SMILES with the R group present, it could take the SMILES and depict the chemical structure with the R group present. And this also could be done in a variety of ways. Moving on, we also did develop a synthetic hand-drawn like chemical structure implementation. Here I am showing a hand-drawn chemical structure and a hand-drawn like synthetic image generated using RANDepict. The same molecule depicted twice using RANDepict. All these improvements were made in Randepict, is now available in GitHub, and it's easy to use Python package, well documented. You could find it in our repository. Moving on is DECIMER image transformer. So as I previously said, DECIMER image to smiles had some issues with training and the model was not performing well. So we ended up creating a different model called DECIMER image transformer, which incorporates again encoder-decoder architecture, where we use for encoding efficient net version 2 CNN, and for decoding we use the transformer encoder-decoder model. So incorporating these two, then we improved our image depiction. We ended up generating nearly 450 million images. All the data came from Pumpkin, and we generated smile strings for the model to learn how to decode the images back to smiles. And we also included marker structures and augmented images with marker structures. And when we completely trained this model using TPUs, when we tested them on all these 4 different test data sets here, nearly 250,000 images each, DECIMER performs relatively well, and you could see the average Tanimoto for almost all the data sets are nearly 1. And with the marker structure, there is a bit of dip, but still the model performs really well on most of these images. And then the next major point is how well this works on real-world test data sets. Like, we have to benchmark that. In order to do that, we collected a few different open data sets from United States Patent Office, Japanese Patent Office. There were a few data sets published with the Staker et al. Paper with 50,000 images each, and we collected all this, and then we tried to benchmark the models, which is already published, with DECIMER. So there are few tools which are open source and available. For rule-based, we have Ostra, Malvec, and Imago. For deep learning-based, we have Image2Mol, TwinOCSR, and MolScribe. When we compare all the tools on the benchmark data sets, which are clean, we could see DECIMER performs relatively well on all the data sets. And when we look at the error rate, how bad DECIMER fails is nearly 2%, like below Tanimoto 0.3, and Tanimoto similarity 0 are also 2%. Moving on, when we looked at this clean data set, most of the tools perform well on clean data sets. And when you include slight shearing and rotation to the exact data sets, which was introduced by the Image2Mol team from the Bayer group, what they found out, if you include a slight shearing, not big, a slight rotation, like 5 degrees or so, these tools tend to fail on most of the images, which you could see here that most of the rule-based tools tend to drop performance very drastically, but the deep learning-based tools still performs well. And DECIMER, on average, DECIMER performs much better compared to most of the other tools. And again, if you look at the error rate, DECIMER has 1% error, like invalid predictions. And with that, we also had to look at hand-drawn images, how well DECIMER could perform on hand-drawn images. In order to do that, we ended up publishing a data note or data set called DECIMER hand-drawn images. This got published last year in Journal of Cheminformatics. This was a collaboration with Westphalian University of Applied Sciences with 23 students from Westphalian University. They hand drew these images and provided the images back to us. We hand curated, compiled, and made available as an open data set. And how well all these tools perform on data set. In this particular benchmark data set, which we later checked. DECIMER was never trained on any of these hand-drawn images, even though it never got trained on any of these hand-drawn images. The current DECIMER model performs relatively well on these hand-drawn images. You could see the identical prediction is nearly 70% and the average Cunningham is 0.93. Most of the time, DECIMER does get the exact scaffold of the chemical structure right, but sometimes it misses out an atom or two or a functional group. So in order to bring all this together as a single platform, easy to use platform, what we did is we created a web platform called DECIMER.ai, which includes all these 3 different toolkits. DECIMER.ai is now available online. Anybody can use it. If you want to, if you log into DECIMER.ai, it's a very easy to use interface. You could see in the demo here, you drag and drop a test PDF. Within a few seconds, depends on the user queue. It scans the whole PDF and tries to check how many chemical structures present. All the chemical structures will be segmented, presented back to you. Then the image transformer kicks in and tries to generate the chemical structures from the segmented structures present on the paper. So if you are happy with it, you can download the results, you can modify, search on PubChem, and if you think there is an error with the result, you can basically report back to us. How well DECIMER also works on hand-drawn structures, you could see this is a live demo which I did in last year German Cheminformatics conference, where I was sitting in the back row using a 13 times zoom. I zoomed in using my mobile phone and tried to capture the structure which was presented by the presenter there. And DECIMER could immediately recognize and try to generate the structure into a computer readable file format. And we use a catcher window here. So if somebody thinks, okay, there is something wrong, our group is missing, you could immediately edit the chemical structure and download the data set. So with this, we thought it would be really useful for most of the dataset curators to use DECIMER to get the data much faster into their databases. The whole toolkit and DECIMER.ai is currently available as a preprint. The DECIMER.ai repository also available on GitHub. DECIMER is a Docker image as well, so anybody can download the Docker image and try to run locally also. With that, I would like to acknowledge my team. My PIs, Professor Christoph Steinberg and Achim Zilesny, and the wonderful team here in Jena, and also my funding sources and Google's TPU Research Cloud. That's all. Thank you. So ready for questions?
Sorry. Thanks very much. Yes, I think we could take a couple of questions. Does anyone on the chat have anything they'd like to ask? Or in the room? There's someone in the room. I'm just going to take the microphone over.
Hello? Yeah, this is very nice to work.
I'm not able to hear you clearly, sorry.
Can you hear me at all?
Is it possible to repeat the question, Andrea?
Can you try now?
Can you hear me now?
Yeah, I can hear you now.
Okay. No, very nice piece of work.
Yeah, thank you.
Something that was always nice about the old rule-based methods is, of course, you get the coordinates out. So in all these AI methods, you're generating a smile string, and you know, you're obviously going to get a randomized depiction based on whatever toolkit you're using the back end. Do you think there's any scope to get coordinates out of these in future? I mean, we saw a previous talk about doing 3D work.
We are already working on the coordinate generation. Probably by end of this year, you might have updated DECIMER version where you will have the coordinates as well. So the exact image with the exact representation will be depicted.
Yeah. Okay. And the other more comment was the average Tanimoto is a bit of a weird measure. Like it's nice you put the exact measure. I would probably just stick with the exact. Again, as you still did good on that. But you know, my view is you either get the structure out or you don't. And if you get a group in the wrong position, the answer is that's not very good. So and again, as obviously is, you know, averages can get skewed very easily. So
yeah, that's true.
The old rule-based methods, you know, if they have some truly terrible outputs, the Tanimotors would be very low and would skew the mean. But that's anyway, otherwise very good. Thank you.
Yeah, thank you. The main reason we actually did calculate Tanimoto is that most of the time DECIMER does get the scaffold right, and sometimes it misses out functional groups. But in a user perspective, with DECIMER.ai, you could upload an image, and if something is wrong, you could immediately fix it and download the data. And also, if there's a wrong prediction, you could report it back to us, which we could later consider to improve our models.
Yeah, I was more thinking about bulk extraction. Though. That's, I mean, you should see how fast some people can draw structures. Is that I'm pretty sure they run faster than some AI models. So it's, but yes. Yeah, but absolutely, you're right. You can tweak stuff in Catcher.
Yeah.
Thank you.
Okay.
Yeah. Thank you very much, Kohulan again. I think we'll move on to our next speaker now. So Will Cunningham from Agnostiq is going to talk about the new Covalent platform. And one of his colleagues from Agnostiq is actually here today in Buckley. So if you have any questions and you're coming to the pub afterwards, feel free to ask him. But take it away, Will.
Great. Thanks for the introduction. Can you guys all hear me and see my screen?
Yes. Okay,
great. So my background, admittedly, is not in chemistry, but I've sort of been working adjacent to it, you know, in the past few years or so. So I actually have a background in complex systems, specifically in computational methods. And so I've applied a lot of different methods to a few different interdisciplinary areas. And, you know, since then, I've done a postdoc and then since been working at Agnostiq, working on workflow orchestration, actually. And so these are really general methods that apply to many different fields, but I think it will appeal to this audience as well. So today I'm going to be talking about Covalent. It's an open source workflow orchestration platform, and it's specifically geared towards both distributed and heterogeneous computing. So just to clarify what I mean by that, distributed computing, I think, you know, if you've done any sort of large scale experiments, you're probably familiar with this. If you've used something like OpenMP or MPI or worked with a cluster, you know that, you know, you need to be able to scale software to more than one core, more than one system. It becomes heterogeneous when you start now trying to access these same resources through different platforms or in different regions. And so this is something that, you know, is increasingly common as HPC centers either are integrating into the cloud or beginning to federate across you know, different regional resources. And so it's sort of changing the user experience of how we think about these resources and how we interact with them. So I've become very interested in this topic over the past couple of years in order to really think about how do we make it easy for users to consume these resources, regardless of how complex this compute landscape gets. So if we sort of take a step back and think about, well, what all is out there, we have this landscape of compute, and it's really, like I said, it's distributed, it's heterogeneous, but it's also rapidly evolving. So if somebody wants to keep up with this or understand where to deploy their workloads, it's actually quite difficult. In each of these different cloud providers, for instance, there's many different regions. In each of these regions, pricing is going to be different. Availability will be different. If you're working with multiple HPC clusters, which was an experience that I had, it can be difficult to manage different copies of software across these different platforms and figure out where the latest version is, where your data is, you know, interact with different schedulers, et cetera. So the point is, it's the kind of situation where rather than interacting with just one of these components now, we're starting to think about multiple components or even this entire landscape as a whole. And as I mentioned, a lot of HPC centers are starting to incorporate some form of cloud bursting into their deployment models, meaning when the cluster is at capacity and the queues become very long, some jobs get offloaded to the cloud, whether it's AWS or Azure or Google. And this is something to both increase stability, but also give access to new or perhaps novel resources that may not be available on the cluster itself. So as an example, in the previous talk, Kohulan gave a great example of how he needed to use TPUs for a particular experiment, so switching from GPUs to TPUs. And so this is basically the problem that we're trying to understand, is how much work is involved in that decision to move to a cloud provider, access these resources, and continue on with research in an efficient way. So ultimately, without any sort of software or tooling to deal with this, it can become quite complex. There's APIs to deal with, different IAM schemes, software and data management. And what we're trying to achieve here is a unified view of the resources, the platforms, and the schedulers that manage all of these. So if we think about, for somebody entering this space brand new, what are some of the decisions that they're going to have to make? How complex can it really get? And again, the goal in mind here is that the software you write today is going to be reproducible. It will be able to be used by somebody 3 months from now, 6 months from now, or 2 years from now, with minimal changes. So we need to think about, how does a task run? Which platform is it going to run on? Where is a task going to run? In the case of one cluster or another cluster, or one cloud region versus another cloud region, there are lots of choices. How are your tasks going to be packaged? Oftentimes in HPC, we see condos becoming popular, but container-based methods through Docker and Singularity are also quite popular in different spaces. And so, it's important to be able to support this in a unified way. And then we need to think about, how is data shared and how is access managed for different users, both in a collaboration and then externally in terms of third-party access as well. So what we're trying to do here through this tool, Covalent, is to close the gap between all of these different degrees of complexity. So on the left-hand side here, there's the hardware knowledge, there's the software or operational knowledge, and then there's the domain knowledge. And at the end of the day, somebody who's doing computational research, they really want to focus on the research problem, minimize the time to publication for a particular project. So we're trying to compress this and abstract away hardware knowledge and operational knowledge, so that these are sort of hidden under the covers, and users can say, well, I need, this many CPU cores, or this many GPUs, or this many TPUs, go run it, and the software will run seamlessly and in a repeatable fashion. So most simply, Covalent is an orchestration platform for heterogeneous computing, and it's designed to act as a single entry point into this broader landscape of compute. So this includes anything you can think of. It includes your local workstation. It includes all of the different major cloud-based resources. It includes quantum cloud-based resources as well, as that's another area that's up and coming for distributed access. And it's important that users are able to have visibility into this, because without any sort of workflow orchestration tool, you end up having to search lots of different platforms for logs, manage all of the data by yourself. It can become very difficult. So we provide a nice browser-based user interface so that users are able to get a clear picture of where the data movement is happening, have real-time status updates, regardless of whether one task is on Slurm, another's on Kubernetes, another's on some cloud scheduler. Doesn't matter. You don't have to know anything about how those actually work. You just have to understand that you're interacting with those devices at all. Now, aside from the hardware component, Covalent also supports heterogeneous software. And so what this means is that while we see in some of these newer emerging fields like machine learning and data science and quantum computing, everything is very heavily Python-based. But a lot of legacy codes are not Python-based. They're C++ or Fortran or maybe something else even. And so what we've done is we've designed Covalent in a way that tasks themselves don't have to be in Python. The orchestration layer happens in Python, and most tasks are in Python, but users can also integrate tasks in other languages and take advantage of bindings between Python and these other languages in order to integrate legacy codes with some of the newer codes. So there are really just three concepts to learn if you're getting started with Covalent. The first concept is that of the electron. So like I said, everything is entirely Python-based. So you take a Python function, you put this little one-line decorator on top, ct.electron, and it transforms this function from a regular Python function into a covalent task. It's still executable, but this means that it's going to have room for all of this different metadata to be attached to it each time it's run and processed through the Covalent server. The second concept is that of the lattice. So the lattice is also a Python function, and this is going to be the workflow definition. So if you're familiar with workflows, you know that tasks are sort of organized into a dependency graph. It's a directed acyclic graph, or a DAG. And so this workflow function is going to define the DAG for your experiment. So it's going to be calling all of the different tasks in your workflow, piping data around, moving files, moving software, interacting with backend schedulers, et cetera, through the Covalent server. So as you can see in this example on the left, it's as if you were running this locally in a notebook, except all of this other stuff is going to happen under the hood. And I'll be a little bit more clear on how exactly this works in just a moment. The third concept here is the dispatch. So this is just an asynchronous deployment of your tasks to the Covalent server. So again, if you're familiar with something like Slurm or Kubernetes or other batch schedulers, you'll know that you send a task off. You don't have to wait for a synchronous response. You just sort of poll it. And when you're ready, you can interact with it again. And so we follow a similar model here, except that this is one layer above all of those other schedulers. So it provides, again, a unified interface in order to interact with these resources. So the design of Covalent is a client-server architecture. And so what this means is that you're going to have a Pythonic SDK that's going to be on your local workstation. You're going to use it to construct workflows, to interact with the Covalent server, to inspect your results programmatically, interact with APIs, et cetera. The Covalent server is this intermediary between you, the user, working in your Python notebook, and all of these different backend compute resources. So it includes a dispatch service, which is going to perform, it's going to facilitate all of these interactions, move data around, identify dependencies, execute things in an efficient fashion. So it includes some sort of queuing and scheduling system in there. And then the user interface is going to provide a visual representation of everything that's happening inside this dispatch engine. Now, one of the things that makes the Covalent server really efficient and really lean is that we use a plugin system for these backends. So this means that rather than saying we're going to support everything from A to Z and we're going to pack it all into a server, and most users are going to pick one or two of those out, instead with this plugin system, we eliminate that bloat, and we say you install these plugins as needed, one by one. You can uninstall them as well. And when the server starts, it's going to have access, it'll have an API defined in order to offload tasks from the central server into these backend schedulers. So we have access, we have support to access a wide variety of different backends, everything from more traditional on-prem stuff like Kubernetes and Slurm and PBS, to some of the cloud-based providers. So we have a whole host of different AWS plugins that plug into various services. We have a Google Batch plugin, Azure Batch plugin, and also some plugins for some of the managed hybrid quantum services that are emerging on the market now. So there's Amazon's Bracket Hybrid Jobs, there's Qiskit Runtime. And so these are basically a way to containerize a task that's both classical and quantum, and you ship it off to this managed service, and it will handle the rest for you. I'll also mention that we have a nice custom executor plugin. And so what this means is that as it's open source and we want to facilitate community involvement, users are able to very easily add a new plugin. So if there's a system that we haven't yet thought of or don't yet support, we provide a template so that you can fill in like 50 to 100 lines of code, and it defines the API interface between Covalent server and the backend system. So it's quite easy to do this. There are lots of examples. And we want to minimize the time in order to do this. On the right-hand side here, we see an example of the user interface. I'll come back to this in a demonstration. But the main things to understand here are that we have a visual representation of a workflow as a graph, where each of these nodes is a particular invocation of a Python function. We have workflow level metadata on the left-hand side and task level metadata on the right-hand side. And I'll come back to this in an interactive screen where I can actually play around with it a little bit more. There are also some basic project management features. I think it's no surprise to anybody that has interacted with large-scale experiments. It can be very unwieldy very quickly. We have lots of data. When we're designing or laying out these experiments, we don't obviously know which data will be valuable, which set of parameters we want to save for later, or which experiments we're going to want to save for publication. And so through tagging and organization like this, it can be just a little bit easier to manage some of this data. Covalent supports a growing ecosystem of both hardware and software. So I've mentioned some of the classical and quantum resources. I want to highlight again that because it's a workflow orchestration engine, you can use any of the packages in Python that you would previously be using. And I'll give an example of this again in the notebook. So just as you'd be able to import any of these packages in a regular Python function, you can import them in a Covalent task as well. And then finally, for languages, right now we're supporting, I have Python on here, and this is to indicate if you are calling a task in a different version of Python, or some other module somewhere else, this is supported. If you have tasks in C or C++, you can call those. If you have particular bash commands that you need to run in order to, for instance, compile code or set up an environment, this is supported as well. And then on our roadmap, not shown here, we plan on adding support for Fortran and Julia as well. If there are other languages that you guys think would be interesting, then either message me or talk to Ian after this, and we'd love to hear feedback. So at this point, I'm going to switch over to a notebook, and let's see how far we get. So I'll just mention briefly, we have a nice documentation page on Read the Docs. A lot of what I'm going to be going over is also in here. So if you want to follow along now or afterwards, it's pretty easy to find, just covalent.readthedocs.io. So our quick start guide here is just designed to sort of give a really clear idea of like, what does the code look like? What are the steps involved to actually install and use this tool? Is it easy? Is it hard? What does that look like? We've thought of a lot of different ways to use this tool. So before even getting started, I want to mention, right now I'm doing everything locally in a Jupyter notebook, in a command line as well in some pieces. But we make Covalent very easy to install. So right now I'm describing a pip installation, but you could also use Docker. You can install it as a systemd service. You can install it using Ansible or Terraform in the case that you're deploying it to managed resources as well. So there are lots of options to deploy it with very few steps. So here I'm going to be doing the most basic version of this. I'll just create a Python virtual environment. I'm going to be using Python 3.8 here. I'm going to pip install Covalent just like I would for any other Python package. And then I'm going to run Covalent start here. And so that happens on the command line. This is how I start my Covalent server locally on my workstation. Now, again, it doesn't have to run on my workstation, but this is sort of the simplest out of the box version of this. So in this little hello world example, I'm going to show how you might interact with some of these executor plugins as well. So here I've defined a few different executors. So here, for instance, you see a Slurm-based executor. I've split the arguments here into things that are commented out and things that aren't commented out. This is to represent that some of this information is static, and so it's going to live in a configuration file. You're never going to look at it once it's set up. So it just describes things like authentication and connection details. And then from task to task, when you're moving these around, when you're thinking about resources, these are the pieces of information that you'd be actually interacting with. So which conda environment in the case of Slurm, we have some options here. So if you're a Slurm user, you might recognize that some of these translate over to what you'd be putting in a Slurm submission script. And so the point is, each of these is going to do all of that under the hood. It's going to connect to the machine for you, copy your files, create any submission scripts that need to be created, interact with the backend scheduler, notify you when tasks are done, and then copy everything back to the Covalent server, or in this case, to my local workstation. So the main thing to take away from this is that if you're using one of these plugins to interact with a remote system, you never actually have to log into that remote system. You can just stay on your local workstation, stay in a Jupyter notebook. So here I have basically the same thing, but with Azure Batch, and here another example with a bracket executor in the case that I were doing something on like a hybrid quantum task. So this simple hello world style workflow is just showing some basic math stuff. It's nothing too revolutionary or complex. But the really interesting part here is that if you look at these two lines that I'm highlighting here, that's the only thing that I need to switch in order to first run it locally on my machine and then afterwards run it on an HPC cluster. So it's very straightforward to prototype something locally and then really change just a couple lines of code and then ship it off to a different machine. And if I were, for instance, to find, well, my Slurm cluster that I'm working with is actually kind of overloaded. The queue times are not very favorable. And I just want to either use a different cluster or a different cloud. Again, I can just switch this one line of code here with something else, and the task will be deployed somewhere else. And I don't have to worry about new scripts or versions of those scripts in order to interact with those systems. So I define my workflow DAG using this function here. Basically, it's just regular Python syntax. And then I'm going to dispatch to the Covalent server. In this case, it's just running on localhost because I started it locally. But it's very easy to send things to a different Covalent server as well. This would be more appropriate if you're really running workflows at scale, or perhaps you're working in a shared setting where you have something on a network server in your office and maybe 2 or 3 colleagues are interacting with it. And then you'd be able to just put a host name and port here and send your workflows off to a different server. So again, it's just sort of toggling these 1 or 2 lines of code, and you can completely change how this workflow executes. So I'm going to dispatch it, and then I ask for the result back. And when I print it, of course, I see it's running because I've issued a non-blocking call. And I can go now to the user interface and start to take a look at what's going on. So here we see, of course, just a bunch of green check marks because this executed very quickly. And so the things that I want to highlight, though, are really that through these visual statuses, I can even hide information. And so here I'm just looking at a really minimal version of this that I might want to use for really large workflows where I'm just looking at status information. And so if a particular task fails, for instance, maybe I have a really, really large workflow and something downstream fails, and I don't want to rerun the whole thing. I just want to sort of resume it or make a modification to my code or change some inputs and then resume the entire thing. This is something that's possible through Covalent. So, the main thing to think about here is that if you have a large experiment, or if you're running tens of thousands of experiments in parallel over a bunch of different input parameters, it's very easy to pause and resume, or pause and modify and restart as needed. So it's no longer something that's stressful. So if we expand this back a little bit, we can see, for instance, that this one up here ran on a Slurm cluster. Each of these ran on Azure Batch in a particular region. These guys down here ran on the Dask cluster, which comes with Covalent out of the box. And then there's a post-processing step. And so this is just going to consolidate everything and return the result of my workflow. Now, on the left-hand side, as I mentioned here, we have interactive inputs and outputs at the workflow level. So if I wanted to click on any of these, for instance, I would be able to copy the Python object and go back to my notebook and interact with it. So this sort of implies at the task level, if I click on something, all of this information is checkpointed in the Covalent server. So if I have something that's long running and I break it up and functionalize it in a proper way, anything that's going to be an input or an output to one of my functions will be checkpointed information. This could include very trivial stuff like I'm showing here, or it could include a pre-trained or partially trained machine learning model. So if I resume my workflow, or if I share it with somebody else, they can take a partially or fully trained model and either use it for inference or continue training it, or do anything else with it. And likewise, if the output were, for instance, a Plotly plot, like I'll show in a moment, then we're able to immediately just copy this back to a notebook or open it using the SDK and not worry about where the files are stored or how they're organized. It's just very easy to sort of organize this when it's all visual. So I'll just, let's see, I have a few more minutes. So I'm going to switch over to another notebook. This is an example where we've done another very basic thing, just sort of like a basic quantum chemistry tutorial here. And so we're using the atomic simulation environment package in order to simulate 2 nitrogen atoms, or N2 molecule, hooking up to a copper slab. So we're just going to be using this package here, ACE and Plotly, for the result. So this is something that previously I had offloaded to Slurm, but this time I'm going to be running it locally. And so the things that I want to highlight here, again, these are just the 2 lines that I would need to swap in order to go from one backend to another. And then we're going to be returning a plot as the result of this. So after I dispatch this to the Covalent server, I'm going to issue a blocking call to wait for the result. During this time, I can close the kernel, doesn't matter, I don't have to wait for it. But I can just sort of monitor the task in real time. And you can see that these workflows get very large for anything that's substantial. And so it then becomes important to actually have good ways to visualize and track information and understand where errors originated, especially when you're running this at scale. So if I go back here, I can see that the result, because it's a plot, I can just basically run this here. So I have my job ID run, and then I do run.result, and it's going to give me a plot as the output here. And so because I've included a sufficient number of data points here, you can see that, in fact, it's a very smooth curve here. So before I conclude here, I just want to highlight a few more things, in terms of features that you might be interested in. So the first thing here is that we support all sorts of different types of file transfers in order to automate data pipelines. So you can imagine that if you're working with big data, you don't necessarily want to copy everything back to the Covalent server for checkpointing. For very large files, if it's on the cloud, you're going to pay for egress. If it's on an HPC cluster, maybe it's just going to not upload or download very quickly between your workstation and the remote machine. So this example here is showing how you would inject files into a task before and afterwards. So here we use an rsync strategy. We also have other strategies if you're connecting to different, particular object storage solutions. And so here what I'm doing is I'm specifying particular files. One will be an input file and one will be an output file, meaning one of them is pulled in from some object storage beforehand, and it's used during the course of my computation. And then afterwards, a second file is going to be copied back to my cloud storage after the fact. Now, the advantage of organizing the code in this way is that you can separate out those operational tasks from the actual logic, the computational logic for your experiment inside this task. So it becomes easier to write unit tests, to manage code, and to really separate out these pieces of code that really have separate concerns. The second thing I want to highlight here is that we can document software dependencies. So here I'm saying that this particular task is going to need a particular version of NumPy in order to run. So what I'm doing here is using the deps pip object. This means that it's going to either check that using like a pip check in order to see if it's installed before the task runs. And if it's not installed, it's going to attempt to install it, or it will fail the task. The other advantage, besides being convenient, is that when this task reruns at a later date, if you want to re-execute the workflow or share it with somebody else, you know the exact versions of these packages without any further documentation anywhere else. So again, you can go to this user interface and see this information and share it with somebody else. And for every particular invocation of your code, you're going to have this information. The third example here is workflow triggers. So this is particularly useful for stream-based processing if you have information that either is coming in on a schedule or based on particular events that are triggered. So here I have an example where I'm using a directory trigger. So as files come in or as files are modified to a particular directory, it's going to execute the workflow each and every time. Likewise, if I'm doing some recurrent machine learning training, I could just trigger this on a schedule, maybe once a day or a few times a day, and it will retrain my model based on the most recent data. And then finally, one of the most interesting features that we support is dynamic workflows. And so this means that the actual structure of this dependency graph is going to be determined at runtime based on the outputs of prior tasks. And so this means that users can have all sorts of complex logic that they might not be able to have in other workflow tools. So an example here, there are lots of different dynamic things you can do, but here I'm showing an example where the degree of parallelism is actually going to be determined at runtime. So my first task is going to do some preparatory steps, whatever that may be, and it will return, among other things, a piece of information that will tell me how many jobs I want to spawn in the next task. This could be based on available resources. It could be based on algorithmic constraints. How well does my problem actually parallelize? And then I'm going to send it off to this nested workflow here. So it's a sublattice or a workflow within another workflow. And so we can see here that the number of tasks in this interesting function f here is going to be determined at runtime, and it will be essentially the number of jobs here. And so we can, aside from doing things like dynamic parallelism here, you could do things like dynamic cloud bursting. If you're able to query availability of resources, you can do lots of interesting things here. So with that, I think I'm about at time, so I'll pause here and see if there are any questions. Thanks.
Thanks very much, Will. Does anyone have any questions in the audience? Hi, Noel. Do you mind bringing?
Hi, Will. Thanks for that very nice presentation.
Thanks.
Really liked your slides and the way you explained the whole thing. One aspect you didn't touch on is, and it always makes me very nervous when I hear a company talking about an open source tool. It looks very nice, but is there a business model behind it? If you can share, willing to share that.
That's a totally fair question. And we actually, this is a somewhat common question. So you'll notice that one of the things that I didn't describe here is managed infrastructure. So one thing that this open source tool does not come with is hosted infrastructure. So like you have to come with your own access to a Slurm cluster, or if you're using one of these cloud accounts, you have to come with your own credentials and pay your own bills and manage your own resources, et cetera. We do have, we just recently announced a hosted offering for Covalent. So this means that if you wanted to run workflows and basically say, I don't have access to any HPC clusters, nobody on my team is a cloud engineer, so we're not going to set up and manage our own cloud accounts. Or maybe we do have cloud engineers, but we're focused on building something else. A hosted version of Covalent comes with the infrastructure built in. So somebody says, here's my workflow, this task requires 8 GPUs, you send it off to hosted Covalent, and it goes and finds the resources and executes the code on your behalf. So that's what the business model for it looks like. Obviously there are extensions of that to enterprise based on particular use cases, but we, very much support the open source community. And so to the extent possible, we want to, make this robust and work well for the research community and for open source users in general.
Thanks. That makes me a lot less nervous hearing that. Yeah, makes sense.
Thanks.
And there's one question from the chat. Does Covalent support Perl codes?
Oh, that's a good question. You got me there. We do not support Perl. If that's something where there's a high demand for it, I haven't used Perl in a while, but I'd be happy to write the integration.
I think there is a lot of legacy bioinformatics code, which is
okay. Yeah, that's really helpful to know. I mean, it's sort of a balance between all these competing interests as we hook up to a lot of different systems, different communities. But if Perl is something that is relevant to this community, then that's something we can take a look at.
Really great to hear from you, Will. I think we will wrap up there. And if anyone has any questions, feel free to drop one of the speakers an email. Their emails are on the website, I think, cmf.net. But for now, we will decamp to the pub. So thanks very much, everyone, for listening, and see you next time.